Hi everyone. In today's video, we're going to continue on our ideas from 3.1a, which was just the big idea was this new term called the derivative. Yesterday was mostly the algebra associated with it. Today we're going to talk about it visually, and we're going to look at a whole bunch of graphs. A recommendation, if you do have some colors in your bag, I would recommend having two colors. I'm going to use red and blue, but that's just because those are pretty accessible in my menu here. You can use any two colors you want. So, last night, or whenever you watch the video, we defined this new thing called the derivative, which describes the slope of some original function at every point. So, our first task here is we're given 4 functions and 4 derivatives, and our job is matching up which derivative goes with which function. So here's how we're going to think about this. Remember, the derivative describes the slope at every point. So how about this? If f, the original function, is increasing, it would have to have a positive slope, right? And if the slope is positive, wouldn't that tell us the derivative would also have to be positive at that same x value? So one of the things I'm going to do is I'm going to look at these 4 functions. I'm going to find the intervals where they are increasing, and then I will match them to the derivative functions that have positive y values at those places. I'll show you what I mean in just a second here. Let's get down the converse of this statement as soon as my pen starts working. There we go. So the converse of this would be if f is decreasing, this is where our second color comes in handy, then its slope is negative. Therefore, its derivative would also have to be negative because the derivative tells you the values of the slope. So what I'm going to do is I'm going to look at these 4 original function graphs and discuss where are they decreasing, where are they increasing. So let's start with increasing. If I'm looking at this first one here, this one on the top left, it's certainly increasing. Look, can I zoom in? I can. Hooray! So it's definitely increasing in this little region right here. And then again over here. But in the middle there, it's decreasing, decreasing, decreasing. It increases for a little bit, decreases for a little bit, then resumes increasing. So when I go looking for the derivatives, I'm going to look for one that is initially negative, then positive, then negative for just a little bit, and then ends up being positive again. Let's do this for all 4 graphs before we try and start matching them to the derivatives. So let's go back. So our sinusoidal one here looks like it's increasing definitely in the middle. And, well, that's about it. Looks like it's kind of decreasing everywhere else, right? Oops. There we go. For our quadratic, it's increasing to the right of the vertex. It is decreasing on the left of the vertex. And then for our cubic, it starts out increasing. Whoops, starts out increasing. Decreases for a little bit, increases some more. And decreases right there in the middle. This is why it was so important in Algebra 2 and last semester in pre-calc that you describe increasing and decreasing as a left to right idea. That way we all agree where the slope is positive, where the slope is negative. Okay, so now let's go down to the derivatives. So let's kind of do the same thing. Now remember, if the derivative is positive, the original slope, if the derivative is positive, the original function is increasing. So like on graph A, the derivative is positive in these two intervals. So these two intervals right here are where f is increasing. And then this little interval here, because the derivative is negative, that would tell you f's slope is negative. That's where f is decreasing. So let's match that up with one of our graphs. So where do we have one that is originally increasing, then decreasing, then increasing again? How about this fourth one? Increases, decreases, increases, increasing. Well, positive derivative, because the original one's increasing. Negative derivative, where the function is decreasing. Positive derivative, where the function is increasing. So these two go together. Let's repeat that for the next couple. Okay, so for graph B, it is positive in these ranges, or I guess these domains. So again, where the derivative is positive, the original function is increasing. And then wherever the derivative is negative, the function's decreasing. Sorry, this is getting messy. So we're looking for a function that is originally decreasing, increases for a while, decreases a tiny bit, and then increases off to the right. Which, scanning our three options, how about this first one? Decreases, increases, decreases for the tiniest little bit, then increases off to the right. Let's see. For our third derivative, it is positive in this region, just to the right of, well, a little bit bigger than 1. That's where f is increasing. Do you have to write this out every time? No, I'm just really trying to hammer this point home because it's easy to get these backwards. So our derivative is negative here. It's below 0, so that's where the original function is decreasing. So let's try and match that up to one of these. How about the parabola here? It's decreasing, then it's increasing. That would match our graph C. And then, well, process of elimination would make this last one D, but let's just verify it real quick. So here is where our derivative is positive. That would be where f is increasing. And then here's where our derivative is negative. And that would be where our function is decreasing. So then let's go double check, make sure our last one is actually doing that. Yep, there it is. Decreasing, increasing, decreasing. So we did it. Let's turn the page. Okay, so this time I've given you a function. Here's our function f of x. And our job is to sketch a graph of the derivative. So we're going to create a graph of the derivative f prime of x over here. Let's keep doing the same thing. Let's just kind of point out where the function's increasing, decreasing, because that'll tell us where the derivative needs to be positive or negative. So I see our original function is increasing on these two intervals. And then I see it's decreasing right there in the middle. And maybe also worth noting is, how about at these 2 points, it changes directions. If it changes from increasing to decreasing, couldn't we argue that right there at these 2 green points, the slope should be 0? Hopefully that's I'm trying to think of a different way to argue that to you other than, well, it's got a negative slope where I made it red. It's got a positive slope where I made it blue. So to go from a negative number to a positive number, you'd have to pass through 0. Hopefully that sounds reasonable. So I'm actually going to start my graph with those 2 points. So at x value 0, the slope was 0. And at x value 2, the slope was also 0. In between those 2 points, the function was decreasing, which means that the derivative would need to be negative. So I need, I don't know, something like this. And then outside of those 2 points, the original function was increasing. So the derivative would be something positive. Now that's weird. Look at this, look at this, look at this. So, well, observation. F of x was, or I guess is, whatever, tenses are hard, cubic. And f prime, the derivative, looks quadratic. Huh. We'll come back to that. Let's look at our next one. So same thing, sketch a graph of the derivative of the function below, state where the function is not differentiable. Whoa, not differentiable. That's a new idea. Let's start by reminding ourselves, hey, we were given the original function. Our job is to come up with the derivative. And now this time around, we can actually calculate the slopes. The up above, we kind of eyeballed this a little bit because the graph was curvy. Here I got a whole bunch of straight lines. Diagonal lines, I should say. So let's actually draw this graph as precisely as we can. So on this first interval, the function f is increasing, and I also see what rise 1, 2, 3, move over 1. So the slope here is 3. Now over here, the function decreases. Whoops, kind of missed it there at the end. And it sure looks like the slope is -1. Over here we got a horizontal line. The slope of anything horizontal is 0. And then finally the graph ends by increasing. And 1, 2, 3. Looks like again the slope is about 3. Now, what's kind of questionable, purple, there we go. What's kind of questionable are these corners here. What would the slope of the tangent line at a corner be? I mean, could I draw the slope like this? Could I draw the slope like that? Could I draw it horizontal? I could draw it more slanty. It's kind of not good, right? Well, we will come up with a more rigorous definition in the next section, but basically, for now, all you need to know is if you can't draw a tangent line there, that is where the function is not differentiable. Or in other words, the derivative doesn't exist. So let's leave ourselves a little note here. Note. The slope doesn't exist at x values -3, 1, and 3 because you can't draw a tangent line there. Therefore, we will say that f of x is not differentiable at those points. I'm only putting it in quotes because it's like a new term for you. Those aren't suspicious quotes at all. So, all right, let's draw our graph then. So from x is -5 to -3, we had a slope of 3. So there's our slope of 3. Slope is typically defined over like an interval, so I'm also not going to include this endpoint over here, and later on we won't include this endpoint either. Let's see, up next, the function decreased with a slope of -1 from x is -3 until x was +1. Again, it decreased that whole time with a slope of -1, so our derivative would be -1 that whole time. From there, the slope was 0 for a while, between 1 and 3. And then finally, the slope was +3 again from 3 until the graph ended. And so again, I'm going to make an argument. We're not going to talk about the endpoints here because slope is typically a two-point idea. And, well, slope at an endpoint of a graph is something we'll talk about in a future section. All right, let's turn the page. In example 8, I'm happy to go in reverse. It's kind of like I gave you the answer. The graph below represents a graph of the derivative f prime of x. So there's our derivative. Our job, draw the original function. So our job is to come up with f of x. Oh, and we're given a point to help us out. So f of 0 equals 1. So I have to have some point right here at 0, 1. Well, let's kind of step through this, I guess, just backwards, how we have in the past. Looking at the derivative, I see the derivative is negative. Whoop, hey, you were supposed to be red. I see the derivative is negative in this region. It's still negative over here. It's still negative up until about 3. The only place that might be interesting is right here. The derivative is 0. Then the derivative is positive in this region. So where the derivative is positive, that would be where f is increasing. Where the derivative is negative, that would be where f is decreasing. And at this point right here, looks like there's one little point where the slope is 0, maybe at, whoa, that was weird, maybe at where x is 0. So then, before we just start sketching here, let's come up with a plan, maybe from left to right. Okay, so from left to right. Initially, f's got to be decreasing until x is 0. At x is 0, the slope is 0. So it's got to like temporarily level off. Then the derivative was negative again, so f resumes decreasing. Until it switches to increasing at x is 3. To which then it increases off. So let me get my handy dandy colors here. Well, might be more confusing. Well, let's just try and match it up with the colors. Okay, so until this point, so from the left, the graph is decreasing, but it's got to level off, so we have a, something that's kind of horizontal there. And then it resumes decreasing until 3. So how about something like that? Does that work? I think it works. And then at that point, the function switches to increasing. Oh, hey, look, by the way, there's another point where m is 0, so that's another way, to show that it's got to 0 off, or be horizontal. And then function increases until we run out of graph. So you might be thinking to yourself, is this point significant at all? Because, I mean, the derivative changed directions. Well, you have to be careful now. Remember, we're at this point, we're really just looking at the sign on the derivative. Sometimes we've looked at the numbers if it's convenient. Right here, the fact that this is a minimum really just tells you that is where the slope is most negative. So if you were being really careful with your graph, we should have had the steepest part of the line somewhere around x is 2. So you can see I missed it a little bit. The steepest part of my line is around here, but pretty close, and we were just sketching. We will revisit this idea, I believe it's not until chapter 4. So we will talk about it before you head out for the summer. But anyway, I think this is a good graph. Let's finish up here, because I know we're running long. And the pen stopped working. There we go. Okay. So, example 9. Let's get a graph of a continuous function f given a point. Okay, so we've got a point again. Let's make sure we get that on our graph. 0, 2. And there's our derivative. Okay, so this means left of x equals 1, slope equals 1, and then right of x equals 1, slope equals -2. Notice we don't know what the slope is at x equals 1 itself. So the slope really wasn't defined for us. Whoops, let's say that. Let's leave ourselves a little note. Slope wasn't defined at x equals 1. So really, we might have some point where the function is not differentiable, kind of like we did in the previous example. Okay, so to the left of 1 here, our slope was +1. So there's my slope of +1. And then to the right of there, I've got a slope of -2. There it is. And hey, just by looking at this graph, oh, by the way, I had to connect the two because it said continuous function. Kind of a big thing there. So that's why the two had to meet up at this point, because the function was continuous. But look, we have a sharp turn right there. So kind of like we did in which example was it? I think it was on the first page. Nope. Shoot. Where was it? Ah, it was on example 7. So see here how we had those points where the derivative didn't exist? Same thing here. We weren't given any information about that point. Hey, maybe because it doesn't exist or it doesn't define. Anyway, that is all for today. Have a good one. See you tomorrow.